can do presentations. So quick reminders. First of all, if you are pre-recording your presentation, it is due at noon. Thus far, I have 1 submitted. I need more than 1 submitted. If you are having problems with YouTube, send me an email. Let me know. Daniel.
Did you get mine?
I do not believe so unless you submitted it in the last 2 minutes.
Okay, well, I put it in the comments. I uploaded it on like Thursday.
Okay,
because
where
I can't
did you
submit. I put it in the submission section where the comments.
Presentation feedback or presentation?
Presentation.
I don't see
Just
it.
the link. Okay.
No, I just have 1.
Can I just email you the link?
Sure,
Because
you can email me the link. That's fine.
Okay,
Yes.
thanks.
Yeah. Oh, comments.
Yeah.
No.
Oh.
Wait.
Okay.
Hang on. Sorry. Oh yeah, there it is. Okay. Yes, I see it in the comments. Okay. Yeah, but can you email me the link too? That would be helpful. Okay, I have 2. I need more than 2. So if you're pre-recording your presentation, that is due at noon today. Please and thank you. Homework is also due at noon today. The homework last stuff is also due at noon. Thus far, I have 9 submissions, and there are more than 9 of you in class, so I need more of those. Remember PDFs, please and thank you, PDFs. Anything else for other logistical questions before we get into presentations? Okay then. Mandy, you want to start? We'll just go in order again.
Sure, that sounds good.
Okay. And again, I will send you a private message if you are at 12 minutes, but anywhere from 8 to 15. So.
Okay, sounds good. Okay.
Okay.
I don't know if I want to hide this or not. I guess I will. Okay, ready?
Yes.
Okay, so the topic that I was researching for my paper was DNA cryptography. Oh, do I have to click? Oh, okay, there we go, sorry. So just a brief introduction, DNA cryptography is a kind of interdisciplinary subfield of cryptography that uses molecules of DNA and biological techniques to develop secure cryptosystems. So DNA is the methods that's used to store the message as well as transmit that. And then biological techniques are used to perform encryption and decryption. So it's a really new field, but I think it provides a lot of promise as computational tools improve and stronger cryptosystems become necessary to prevent attacks. So the goals and requirements of a DNA cryptosystem, but I thought that a few of them were worth mentioning. So as always, Alice and Bob need to communicate securely without Eve compromising the message. And according to Kirchhoff's principle, the security of a cryptosystem must depend on the key and not the implementation of the cryptosystem. I think this is worth mentioning for the subject of DNA cryptography because I'll be going over a couple of biological methods and protocols that are kind of complicated, especially if you aren't a biology person, but you have to assume that Eve knows those techniques and would know how to carry out those protocols. So even though you have these biological techniques, you still have to assume that the security depends on the key. And so since the security depends on the key, you have to assume that Alice and Bob are capable of securely sharing the key, whatever that biological component is. So a brief introduction to DNA. DNA stands for deoxyribonucleic acid, and it's the carrier of genetic information in all living organisms. So you can see this probably very familiar picture on the right, where DNA is composed of 2 polymers of nucleotides, and the 2 polymers wrap around each other in the shape of a helix, which you're all very familiar with. And then the shape of the helix is formed by these base pairs that bond together. And these base pairs form together in a complementary way, such that adenine always binds with thymine and cytosine always binds with guanine. So this complementary structure of DNA is what actually makes it really useful as a component of a cryptosystem. And so I'll be talking about how that complementary structure is used in these techniques. The compact structure of DNA also allows it to store large amounts of information. So if you just think about a simple example, if you have a sequence of DNA that only has 5 bases, you still have over 1,000 different combinations of those 5 different DNA bases that you could have. So you can really pack in a lot of information into a small amount of DNA. So 1 gram of DNA can actually hold 10 to the 8th terabytes of data. So the biological techniques are of these DNA cryptosystems is what I'll be talking about next. So while modern cryptography depends on mathematically difficult problems, DNA cryptography depends on biologically difficult techniques. So all semester we've been talking about hard problems like the discrete log problem, and those have analogous difficult problems in biology. So a really prevalent technique is called polymerase chain reaction, which is abbreviated PCR, and it is used to amplify specific DNA fragments. I'll be talking about this a little more in a couple slides, but when you have small amounts of DNA, they're not often detectable because they're in such small amounts. So you need some method of amplifying the sequences that you want to detect so that they're actually at a large enough level. The second technique I'll be talking about is the use of DNA chip technology. And DNA chips consist of probes embedded on a solid surface. So you have this flat surface and all of these probes embedded in it. And at each probe, there is a specific single DNA sequence. And so with those vertical DNA sequences, when you wash over a solution of DNA and there are the correct sequences, those complementary single strands will bind to the probes on the DNA, or bind to the probes on the DNA chip. And then you can use various techniques to detect where those sequences of DNA have bound to the chip. So PCR is one of the more prevalent techniques. And the reason that PCR plays a component in the security of a DNA cryptosystem is because PCR requires the correct set of primers to identify the DNA sequence of interest. So this diagram at the top is just an example of the first cycle of PCR, where you have this double strand of DNA that you're interested in, and you want to amplify this lighter gray region. And you have to have the correct primers because the primers will bind to the start of that DNA sequence. And then you use DNA polymerase, which is an enzyme that will bind to that location where the primer is on the sequence, and it will travel down and add all those complementary base pairs so that you reform that double helix and you've doubled your amount of DNA. And this picture on the bottom is just what happens after many rounds of PCR. You double the amount of DNA every single time, and you ultimately run enough cycles so that you have a large enough amount of DNA that you can detect. The reason that PCR is secure and these primers need to have the right sequences is because if you have a different set of primers, it's not going to bind to the correct region on the DNA, and you're going to copy a completely random and irrelevant sequence of DNA that you don't actually care about. So if Alice was just going to try a bunch of different primers, she can't really, there's so many different possibilities of primers that she's not going to make the correct sequence primer that Alice and Bob have both shared. So a simpler example of a DNA cryptosystem was proposed by Cui and others, and they proposed a cryptosystem that utilizes RSA and polymerase chain reaction. So the keys in this system would have 2 levels. It would have the RSA keys that we're all familiar with and the primers used in PCR. So the protocol would involve encrypting the plain text into ciphertext using RSA, and then that ciphertext would be encrypted into DNA ciphertext using an alphabet of nucleotides. So that would be having each number or letter in the plain text or in the ciphertext after it's been encrypted by RSA. Each letter or number there can be represented by a specific DNA sequence. So you kind of have this mapping, and you can translate the ciphertext into DNA ciphertext. So now that the message is in the form of cipher DNA, Alice will attach the primers to the ends of the cipher DNA so that Bob can run PCR. So if you have the message here where the gray part is your message of interest that Alice and Bob want to share, she needs to attach the right primers so that Bob can use the complementary pairs to bind to that location and actually copy and amplify the message. Alice can also add unknown DNA to the solution of the message DNA, and send this mixture to Bob so that there's a little more confusion and the correct primers become even more necessary to amplify the correct sequence amidst all that unknown DNA. A more complicated but also really interesting example of a DNA cryptosystem involves the use of a DNA chip. So Gahani proposed a cryptosystem that can encrypt 2D images using a library of DNA sequences and a DNA chip. So the keys in this cryptosystem would be the DNA chip and the library of DNA pads. So those are things that both Alice and Bob have, and they both know the correct sequence of DNA and all of those things. So the library of DNA pads consists of all these short segments of DNA, which I'll be calling a pad. So one sequence or one pad has a plain text and a ciphertext sequence. So that's this part on this diagram right here. So you have a ciphertext sequence and a plain text sequence. And so when Alice would perform encryption, she would wash the solution of DNA over the DNA chip, and the complementary sequence in that ciphertext pair would bind to the correct probe on the DNA chip. And based on the locations of where DNA has bound, that's how you get these images. So you could have DNA binding in all of these black regions, and you wouldn't have any DNA binding in these white regions. And that's how you would create that picture. And then Bob would ultimately perform decryption using the same DNA chip with the same sequences located at the correct positions, and he would be able to recreate the picture on the right side. The picture in the middle is an example of what would happen if you tried to perform decryption with an incorrect chip. You'd really just have DNA binding to completely random locations on the chip, so you can't recreate the image. So the way that encryption and decryption work on this system is diagrammed by this. So Alice and Bob, remember, both share that library of DNA pads. So Alice would have her DNA chip and wash DNA over the DNA chip so that there are DNA sequences bound to all of the probes. And she would put a mask over the DNA chip, and that's how she would make that picture. So the mask right here is an opaque region that represents the dark regions of the picture, and there's a transparent region here. And so she would flash the DNA chip with a light, and so these areas under the transparent regions unbind from the DNA sequence. And so that leaves just these half portions of the DNA pads. You can see that the plain text pair right here, or sorry, I think the ciphertext pair right here is still bound to the DNA chip, and she only has the plain text pairs. So she would send this mixture to Bob, and he would have it over here. And then he needs to recreate that plain text ciphertext pair sequence so that he can wash it over the DNA chip. He needs to recreate these dotted portions. So he combines that with his library of one-time pads, and these ciphertext sequences bind to the library of one-time pads, and he can use PCR to add the complementary strands, and it will ultimately recreate that plain text ciphertext pair, and he can wash it over the DNA chip, and those DNA sequences that he just created will bind to the correct locations on the chip, where you can see over here, that was where they were bound on Alice's side, and they'll be bound on Bob's side again to recreate that picture. So there are some limitations to DNA cryptography. It's still a fairly new field of research, and a lot of these examples of DNA cryptosystems aren't ready to be implemented practically. They're not really designed in a way that they'd actually be included in like a huge scale communication system. There are also biological components of the limitations. The stability of DNA relies on environmental conditions. So you need to make sure that the DNA isn't going to become damaged when it's being transmitted from Alice to Bob. And the contamination of DNA can, at any point, can also lead to changes in the DNA sequence, and this would lead to altered messages. And lastly, the manipulation of DNA sequences takes time. You have to sequence the DNA to make the sequence of nucleotides that you want, and you have to run things like PCR. And so this takes a lot of time, especially when you compare it to efficient algorithms and calculations like RSA. So while there are issues to address in DNA cryptography, I think it provides a very promising avenue of research that people should continue pursuing. It can add to the security of modern cryptosystem because we saw in the first example how it can provide 2 levels of security when it's combined with modern cryptography techniques. So further development of the proposed techniques and improvements in DNA computing can ultimately lead to secure and, in my opinion, really cool and interdisciplinary cryptosystems. And these are my sources, the ones who published those 2 DNA cryptosystems that I talked about.
All right, awesome, thank you. Any quick questions before we head to the next presentation? Maybe time for one question, maybe? Daniel, yeah.
What does anneal mean when you had that in a lot of?
Yeah, so that just means like basically it binds to it.
Oh, okay. Thanks.
Okay, that was a really quick question. Anybody else? Other questions for Mandy?
Yeah, I've got one real quick, I guess. Um, so obviously you say it takes time, and I don't know much about biology stuff, but I assume it's never going to be as fast as just running some calculations on a computer. So what would be an area that this might be practically used in the future, considering that it does take a little bit more time, like a
Great.
lot?
That's a really good question that I don't really have an answer for. Like all the papers that I read were really just examples like these where they like proposed a crypto system, and it's not, none of them are really like, oh, this should be implemented in this situation for A, B, C reasons. It's just kind of people thinking of their own ideas about how you can use these things in cryptography.
Awesome, thank you. All right, we'll have you stop sharing your screen, and I'm gonna pause